Okay, next exercise 48. Here we have a commutative ring R without any zero divisors. We have to prove that its characteristic is either 0 or a prime. Now the claim is not exactly true. We need another additional condition for it to be true. So let's first address that and then start the solution. In the solution itself we start like that. In order for the claim to be true, we have to additionally assume that R is a non-zero ring. That is because the characteristic of the zero ring, which has only one element, is 1, and 1 is of course neither 0 nor a prime. So that's why we are also putting this additional restriction on R. R is a non-trivial, it's a non-zero ring. Okay, now if the characteristic of R is 0, then of course we are done. We do not have anything to do, anything else to do. So we assume that the characteristic is not 0, that means it's a positive integer, is a is some positive integer n. Now since R is a non-zero ring, so this n cannot be equal to 1 because the zero ring is the only ring having characteristic 1. But n is already a positive integer, so n has to be greater than 1. Now our aim is to show that n is a prime number. Suppose it is not. Suppose n is not prime, then n has a n is not prime, but because n is greater than 1, n will have a prime divisor or a prime factor. So n has a prime divisor p such that this integer a, which is n divided by p, is greater than 1. That is because n is strictly greater than p. N is not equal to p. N is not a prime. Okay. Now choose any element, any non-zero element in R, and we are able to make such a choice because R itself is not the zero ring. So there is something in R besides 0. then by the rules of exponents in the group R plus, we have P dot A dot X equal to PA dot X, which is N dot X, and that is equal to 0. Now, what does it all mean? Right. This we understand. We have supposed that n is not prime. So, n has a prime divisor p that is less than n, and as a result, this integer n over p is greater than 1. Then what we did, we chose one arbitrary non-zero element x in R. So, that means x is any non-zero element in R. Now what we are saying, by the rules of exponents in this group, we know that the ring R is a group under its addition operation. In fact, it's an abelian group. Now if you forget for a moment that this is an abelian group and treat it just as a group, then in that group, what is this P dot A dot X? In that group, that means that is a general group in which, so we do not consider the fact that it is abelian. That is, we are not going to use the additive notation, but we use the general multiplicative notation. Then this element is this power. It is the pth power of the power x to the power a in this group. And we know that in a group we have the two rules of exponents. One of them allows us to write this as this. And if you translate this back using the additive notation, then this will be just this. Keep in mind that here x is a ring element, but P, N, A, these are positive integers. So what you are looking at in these equations are actually integral powers of group elements. So that's how we have, using one of the, namely this rule of exponent, this. But then PA is of course n, and nx is 0 because n is the characteristic of the ring. So n dot x is 0 for any element x in R. Okay. Now two cases arise. The element a dot x, it's a ring element. This element may be 0, it may not be 0. Let us see what happens if this element is non-zero. If a dot x is non-zero, then the additive order of a dot x then the additive order of a dot x in our ring is P. Why? Let us again write this in multiplicative notation in this group. I have written E here in place of 0 to indicate the fact that this 0 is the identity element in this additive group. Now from this equation, can we say something about the order of x to the power a? Yes. In fact, by one of the corollaries to Lagrange's theorem, well, I am saying this from Herstein's book, but here also in Gallian's book also, Lagrange's theorem implies that the order of x to the power a, from this equation, we get that this order has to divide the exponent p. But the order of any element, when that order is finite in a group, is by definition a positive integer, and the only positive divisors of the prime p are 1 and p. So this is 1 or p. But if this order has to be 1, then the element must be the identity element, and well, this is not P, this is E. For this to happen, we must have this. But if you write this in additive notation, it looks like this. So our condition that a dot x is non-zero then leaves us with only one option, namely that this order has to be equal to P. So that is why we are writing that the additive order of a dot x, additive order means the order of this a dot x element as an element in this additive group, it must be P. But you recall the previous exercise, the one before this, there we proved that in such a ring, all the non-zero elements have the same additive order. So by the previous exercise, all the non-zero elements of R have order P. And what does that mean? If we write that in equation form, P dot y is equal to 0 for all y belonging to R. If y is non-zero, then that's what we have written here above this line. But when y is 0, then also of course P dot 0 is 0. So we now have this. So what does this equation or what does this condition tell us about the characteristic of the ring? The characteristic of the ring from this equation, we can say, must be less than or equal to P. This implies N, which is the characteristic of R, must be less than or equal to P. But that actually creates a problem. Let's see what type of problem. But then A, which is N over P, from the, because of this inequality, A will now be less than or equal to 1, which is exactly opposite, which is exactly not what we have here. This one tells us that A has to be greater than 1, a contradiction. A contradiction to this. So that means this case actually does not arise. It's not a possibility. We must have A dot x equal to 0. Thus, but note that we chose x to be any element in R. So for any non-zero element in R. So for any such element, A dot, that element is 0. Hence, oh, I lost the divider. Anyway, hence A dot y is equal to 0 for all elements y in R. But then, just like before, n, which is the characteristic of R, is less than or equal to A. This, however, is not possible since A is less than 1. No, what am I saying? No, that's not the reason. A is not less than 1. This is where we are getting A less than or equal to 1, but originally A is greater than 1, but that is not why we are having an impossibility here. The reason for the impossibility is this. Because you see, what is n divided by A? If you divide on both sides by A, which you can do because A is a positive integer, then this inequality would give you P less than or equal to 1. That is an impossibility since this implies So now you see that A dot x can neither be non-zero nor 0, but then we have run out of options. So we are now at a dead end. So something must have gone wrong somewhere, and that wrong thing is in the beginning itself, our supposition that n is not prime. So that supposition must be wrong, that is n must be prime. Hence, our first supposition is wrong, i.e. n must be prime. So that is the solution. Now let's see the next one. Let x and y are two elements let x and y will belong to a commutative ring R with prime characteristic P. So X and Y are elements coming from a commutative ring R whose characteristic is a prime P. Then there are three parts. Show that X plus Y whole to the power P is this. Part B is a generalization of this. Show that for any positive integer n, we have this equation. And there is one more part. In part C, we have to prove that this is not necessarily the case if the characteristic is not a prime. Find elements X and Y in a ring of characteristic 4, which of course is not a prime or is a composite integer, such that this is not equal to the fourth power of x plus the fourth power of y. So let's see the solution. So in part A we have to prove this, and in proving this we are going to take the help of the binomial theorem. Now the binomial theorem, just like it is true for, say you want to expand this power using the binomial theorem, and say your x and y are real numbers or complex numbers, then you already know what the binomial theorem is. Now if you go to the proof of the binomial theorem, which normally is done by induction on the exponent, you will see that in that proof only the ring properties of the real number system or the complex number system are used to prove that fact. So and in fact the fact that those systems are commutative rings is what matters in that proof. So that same exact proof works in any commutative ring. So in any commutative ring you have a binomial theorem with that exact form. So that's what we are going to use here. So let us now first see some preliminary things that we will need in that proof. Keep in mind that our ring has characteristic P. So that means if we take a ring element and add P copies of that element, we are going to get 0. So this is how we start for any integer I satisfying these inequalities. P does not divide P minus I factorial times I factorial. Why? That is because since P is a prime, in order for P to divide such a product, P must divide at least one factor. But if you write these factorials out as, using their definition as a product of those integers, all of those factors turn out to be less than P. So none of them is divisible by P. And as a result, P cannot divide this product as well. Okay, so now you are looking at two integers. One of them is P and the other is this. Now what are the positive divisors of P? Since P is a prime, there are only two positive divisors, 1 and P. Among them, P does not divide this, and this of course also does not divide P. So the only common positive divisor of P and this number is 1, and that is why that is also the greatest common divisor. So from this non-divisibility, we have this conclusion. Okay. Now what we are going to do, now we will consider a binomial coefficient, because that's what we want to know how the binomial coefficients are going to behave in this ring, because if we expand this using binomial theorem, binomial coefficients are going to be there in that expansion. Now since this binomial coefficient P choose I, which we know is P factorial divided by P minus I factorial times I factorial, is an integer. Okay, so that is one thing we already know, and in fact we know what this integer is. It is that positive integer which gives you the number of ways of choosing I objects from P objects. Okay, if I objects are chosen at a time, then in this many ways you can do that. So we know that this is a positive integer. It's an integer, that's what matters. Positivity is really not needed. So that is one thing. And also P factorial is of course P minus 1 factorial times P. Now combined with these two things, this relative primality of P and this, then what do you get? And this GCD is 1, we have this dividing P minus 1 factorial. Now I am going to elaborate on this. How exactly are we concluding this? Okay, so from this formula, since we know that this is an integer, that means the denominator divides the numerator. But the numerator is this product. Now we also know that P and this denominator are relatively prime. There is no common factor other than 1. So this cannot possibly divide P. So in order for this P choose I to be an integer, the only thing that it must be true is that this has to divide the other factor, because otherwise it will be a non-integer, it will be a fraction, right? So that's why this divides this. But now you look at this thing, if this denominator divides this, then this quotient can be written like this. This is an integer times P. So that means whatever integer this is, it's actually divisible by P. Hence, P divides this binomial coefficient for all integers I in this range. Now we use the binomial theorem. By the binomial theorem, so the binomial theorem has the same form that it normally has. And in that form, what we do, we are going to write the first term and the last term separately and write the rest of the sum separately like this. X to the power P plus y to the power P plus summation P choose I x to the power P minus I times y to the power I, where I varies from 1 to P minus 1. Now in this sum, if you would have written the entire thing as a sum, then I would have varied from 0 to P. And in fact, here if you put I equal to 0, I mean we do not have I equal to 0 here, but just I am saying in this term if you take I equal to 0, you then get x to the power P. And if you take I equal to P, then you get y to the power P. So we have lost those two terms, we have written them here, and the rest of the thing has been written as a sum. Okay, now you invoke the condition that we are in a ring of characteristic P. So what is going to happen to these terms? And to be notationally correct, I should ideally write this dot this, because P choose I is a positive integer and this is a ring element. And we have decided to write this kind of products because after all this is just an integral power, right? An integral power of this element in the group that the ring is under addition, where the exponent is this. So anyway, so now what we are going to have is this. Because P divides this, so this is a multiple of P. And that is why, since the ring has characteristic P, this sum vanishes. All the terms are 0. So that's why this is equal to the pth power of x plus the pth power of y. So that's how we have part A. Then we see part B. Part B is extremely straightforward. The harder thing that is there in part B, that is the base case, which is just part A. So to prove part B, we are going to apply induction on N. the case n equal to 1 is part A. Okay, so now let's write the induction hypothesis and then do the induction step. So let I already need ink. I don't understand what is happening. This is a new marker and I already refilled before starting the video, but still just give me a moment. Okay, so this is our induction hypothesis. For some positive integer n, then we just straight away consider this power. P to the power n plus 1 is the exponent here, and this element of course can be written like this. Now before I write anything else, let us look at this step carefully. Here also actually I have used a rule of exponent which looks exactly like that rule of exponent we have in groups. However, the operation that we are dealing with here is the multiplication operation in the ring. And under multiplication, a ring is not necessarily, in fact it is never a group due to the presence of the zero element. So what is this thing that we have used here? It turns out that in spite of the ring not being a group under multiplication, this rule of exponent continues to be true. The only thing you have to keep, and which you can prove by induction, the only thing you have to keep in mind is that the exponent should not be negative, which here it is not. And also another thing that has to be kept in mind is that if your ring does not have a unity, then you cannot take the exponent 0, because then it cannot be defined in a consistent manner. But in general, our exponents are our positive integers, powers of prime. So here it continues to be true. Okay, now just simply applying the induction hypothesis, this inner thing becomes this. Now you use part A, treating x to the power p to the power n as one element, say capital X, and this one as say capital Y, another element. So doing that, you get this. Which, if you use that rule of exponent once more, gives you this. This completes the induction. and proves part B. And now we go to part C. In part C, we have to consider a ring whose characteristic is 4, and there we have to find two elements x and y for which the fourth powers do not behave like what we see here in this equation. So for part C, you consider this familiar ring consisting of 4 elements, where we know that the addition and multiplication are respectively addition modulo 4 and multiplication modulo 4. And we also know that this ring has characteristic 4, because if you add 4 copies of every element, you get 0, and 4 is the smallest positive integer with that property. We know that the characteristic of this ring is 4. Now in this ring, and now the ink is coming properly. If we take in place of x and y say 1 and 3, then this is, in this ring 1 plus 3 is 0, so we get 0 if we calculate this power. But this thing on the other hand is 1 plus 3 to the power 4 ordinarily is 81. If you divide that by 4, you get remainder 1. So that means in this ring 3 to the power 4 is 1. So you get 2. This completes the solution. And after this, of course, the exercises continue, but we will continue with the remaining ones in the next Gallian ring upload. And tomorrow we of course do analysis, in which we will resume our solutions to the exercises that come after that y exercise that we saw in the last analysis video. So see you tomorrow with that thing. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.